Okay, so for nearly a century, right, we've had this bedrock idea in quantum physics, the Heisenberg uncertainty principle.
Mm-hmm. The one that says you just can't know everything precisely at once, like position and momentum.
Exactly. There's this fundamental limit. But uh, what if that limit isn't quite so universal? What if it's more flexible?
Well, that's a pretty radical thought.
It is. And that's what we're digging into today. We're looking at some really interesting research, a paper by Pushpendra Singh on unified quantum mechanics, UQM. It puts a whole new spin on quantum uncertainty.
It really does. The core question it raises is, what if uncertainty isn't some fixed cosmic rule, but actually changes depending on the quantum state itself? This dive is all about exploring that how UQM might actually connect the quantum and classical worlds more smoothly than we thought.
Okay, let's get into it. So the big change in UQM, it sounds kind of technical, but it's actually quite elegant. You know the imaginary number that pops up everywhere in quantum equations?
Oh, yeah, square root of -1. Essential, usually.
Right. Well, UQM replaces that E with something called the temporal Hilbert transform operator, nor HET. So it's not a fixed number anymore, it's an operator.
And that simple sounding change has huge knock-on effects. Instantly, the way things like position and momentum relate their commutation relation, it changes. It's not a fixed constant anymore. It involves this new operator, math
Yeah.
operation.
So the uncertainty itself becomes dynamic.
Exactly. It becomes state dependent. It hangs on the average value, the expectation value of this Hilbert operator, grade math.
Yeah. Okay, that's interesting. But here's where, honestly, it gets a bit mind-bending for me. For the usual quantum states, the complex ones we always use, UQM gives you back the standard Heisenberg limit. No problem. Because for those states, Langle-Requian just works out to be I. It recovers the old rule.
Right. Consistent with everything we know for standard quantum mechanics.
But, and this is the kicker, what about real-valued wave functions? Simpler waves, you could say, without that complex part.
Ah, yes.
For those, the expectation value angle-angle dollar can actually be zero. It can just vanish.
And that is the profound point. If Langle-Haskell dollar is zero, then the whole uncertainty relationship changes. UQM predicts zero uncertainty bounds for these states.
Zero uncertainty. So delta X, delta PGAEC. That sounds impossible based on standard quantum mechanics.
It flies right in the face of it, doesn't it? It suggests that for these specific real-valued states, that inherent quantum fuzziness could, in principle, disappear. You might actually be able to measure position and momentum, or time and energy, perfectly simultaneously.
Okay, hang on. Let's make this concrete. Think about a cricket ball just sitting there. Classically, we know exactly where it is and that its momentum is zero.
Right, perfect certainty.
But standard quantum mechanics says there's still some tiny uncertainty, even for a big object. So how does UQM handle this?
Well, if you describe that cricket ball with a real-valued wave function, which seems reasonable for a stationary macroscopic object, UQM says delta x delta p is possible. It basically recovers classical determinism, our everyday experience, directly from the quantum framework. And crucially, without needing wave function collapse.
Wow. Okay. See, it avoids that whole measurement problem issue, or at least part of it.
It certainly offers a different perspective,
Right.
and it doesn't stop there. It also tackles other foundational issues. Remember Pauli's theorem?
Vaguely.
Yeah,
The one arguing time can't be a proper quantum observable like position.
that's the one. It caused all sorts of headaches. But UQM, with its operator-based commutator and the zero expectation value for real states, seems to get around it. It allows time to be treated as a proper self-adjoint operator, even with bounded energy, putting it on a more equal footing.
So wrapping this up, what's the big takeaway here? It feels like this UQM idea is fundamentally reframing uncertainty.
I think so. It suggests uncertainty isn't this absolute law carved in stone. It's more like a feature of how we mathematically represent the quantum state. Complex states have it, real states might not.
Which provides that bridge maybe between the weirdness of quantum mechanics and the predictability of the classical world we live in.
Exactly. A potentially seamless transition based on the mathematical form of the state.
It really makes you wonder then, if something as fundamental as uncertainty is tied to mathematical representation.
What else are we missing? What other aspects of reality might look different if we just, change our mathematical perspective?
It definitely gives you pause. Makes you think about what else we might find if we keep questioning even the most solid-seeming rules.
Absolutely. Food for thought.
Definitely. Something to mull over until our next deep dive.